In fact, here's some of the data from Rutherford's experiments along with the students, and it suggests what is in fact the correct nuclear size. The plot on the left shows a graph of number of scattered alpha particles as a function of scattering angle, and although most alpha particles go straight through at 0 degrees deflection, there is this characteristic curve that Rutherford was able to derive. It goes like 1 over the 4th power of the sine of half the angle of scattering. And one, as a result, sees alpha particles scatter all the way back here at nearly 180 degrees. Well, this shape of scattering angle was seen for alpha particles of a variety of energies. That was sort of independent, unless the alpha particle got up to be a very, very significant kinetic energy. So this is graph on the right is a graph of the scattered intensity of alpha particles at one particular angle, 60 degrees, as a function of the kinetic energy of the alpha particle. And for relatively low energies, these alpha particles follow a particular curve expected from the predictions of Rutherford's formula, because of 1 over the kinetic energy of the alpha, until one gets to a characteristic value out here around 27 MeV. And that's where something dramatic happens. The scattering falls off rapidly, as if alpha particles don't make it out anymore. They even might stick to the nucleus. Well, that turns out to be exactly kind of what's going on. When the alpha particle gets to be too high a kinetic energy, of course, its kinetic energy is such that it overcomes the potential energy barrier from the Coulomb repulsion of the nucleus, and the alpha gets closer and closer to the nucleus. And in fact, it might stick. So this point of departure here can be used to calculate actually the approximate size of the nucleus. In this case, it was lead 208. And that's something I'll ask you to do now, is calculate the approximate size of the nucleus given this kinetic energy of 27 MeV, where one sees the departure from Rutherford scattering. Now the picture here is that I have an alpha particle zooming in. And normally it would turn around and reflect backwards, getting up to only a certain minimum separation. R, and at such a point where all the kinetic energy of the alpha turns into potential energy of the alpha as it gets close to the nucleus. So this happens at such a point where T alpha is equal to K E squared times 4, this will be 2, because the alpha particle has 2 electron charges, over R. So this departure occurs for a particular kinetic energy of 27 MeV, and we can calculate what R that would be. Well, it's useful to know that the constant Ke squared has a value of 1.44 eV nanometers, or 1.44 MeV femtometers. And Z for lead is 82. So this value for R is approximately 2 times 1.44 times 82 over 27. This is MeV femtometers, and that's MeV. 82 over 27 is approximately 3. This is about 9 femtometers, give or take. And so this told us approximately what's the value for the radius.